Good morning, children. For the coming test, that is the test you're going to have on Saturday, that is 29th August. So, as it was written in the syllabus, you're going to have chapter 2, work, power, and energy. Okay, work, energy, and power. But this chapter has 3 parts and quite long. So I thought of taking test only of B and C part. A part you've already given test. So I'm planning to take test only of B and C part. Okay. So quickly we'll do a recap of this. Okay. So B part, different forms of energy. So kinetic and potential, and then their types. Okay. And just the definitions is enough. And gravitational potential energy formula, and there is a concept here. If H2 is greater than H1, potential energy, there will be a gain in potential energy, and that will be final potential energy minus initial potential energy, that is mg H2 minus H1. Okay, then comes kinetic energy. Okay, definition, and then the formula, kinetic energy is half mv square. Then a relationship between kinetic energy and momentum. Okay, kinetic energy is half mv square, momentum is m into v. So if you see the relationship, you will get p square is equal to 2mk. Kinetic energy they represent usually by k, or p is equal to under root of 2mk. Now based on this, there will be a lot of logical questions. Okay, so you already written question number 12 and 13 in your exercise is one example, and even these case 1, case 2, these are also some examples of the kind of questions that you will get based on this. Then comes work energy theorem statement. According to work energy theorem, work done by a force on moving body is equal to increase in kinetic energy. Whenever there is an increase in speed, then work done you can calculate by using this formula, increase in kinetic energy. So you'll have numericals based on this formula. Then coming to kinetic energy, the types, just know the types, that's enough. No, don't have to study in detail, just have an idea about it, that's enough. Okay, then come straight away to conversion of potential energy to kinetic energy. Okay, so many examples practically that you know now. Then we have different forms of energy, and mainly conversion of one form of energy to another. Okay, conversion of one form of energy to other. So from this part, different forms of energy, you get questions only based on conversion of one form of energy to other. You don't have to study these types of energy in detail. You've done it in 9th standard. All that you have to study is mainly conversion of one form. So I have already underlined enough of things. So this will have quite a lot. Okay, dynamo converts mechanical to electrical. Okay, they can ask both ways. Either they can ask, give one example where mechanical energy is converted to electrical energy. So you should be able to write dynamo. Or they can ask like this, what is the energy conversion in an electric iron, electrical energy to heat energy. So like this also you can expect both the ways. So memorize all these things, plus some extra ones are also there that is not in that one. So I think I have marked it and given. Okay, electromagnet, nuclear reactor, fuel, steam engine, explosion of crackers, automobiles. Okay, so all those also you need to remember. Then come to the numericals. So you will have numericals based on kinetic energy and potential energy. Okay, so the first based on potential energy, then you'll have based on kinetic energy, and there are lots of logical questions like this. If the speed is halved, how does its kinetic energy change? Calculate the decrease in kinetic energy if its velocity reduces to half the initial velocity. Okay, so these are some of the logical questions that you can expect. Apart from that, you can have numericals like this also. Okay, so if there is a change in speed and if they ask you to find the work done, then you have to use work energy theorem. Okay, work energy theorem, that is final kinetic energy minus initial kinetic energy, half m into v square minus u square. And don't forget to convert kilometer per hour to meter per second, and kgf to Newton, and minute to second. Okay, so you have to do everything in SI unit. So though kgf is SI, it's better to convert to Newton, then only you'll get the answer in joule. So convert this into Newton. How will you convert it into Newton? Multiply it by 10. Okay, they told you to take g as 10, so 1000 into 10 Newton, and then kilometer per hour to meter per second, what you should do, into 5 by 18. Okay, then 2 minutes multiplied by 60, that will give you the seconds. Okay, then you can find it. So this is what is there in B part. Quite a lot of logical questions are also involved in this, and numericals. Okay, coming to C part, this is mostly theory. So principle of conservation of energy, and you'll have two applications. One is verification of this principle of conservation of energy for a freely falling body. So you will take three positions. One is the topmost, then one middle, and the lowermost position, and then you have to prove at each position total energy is same. Okay, so at some point it will be kinetic energy. At the topmost point it will have potential energy, and kinetic energy will be zero. It has not started moving, so potential energy will be there, but kinetic energy will be zero. And the middle, it will have both potential and kinetic energy. Because it is moving, it has already started moving, it will have kinetic energy, and still it is at a height h above the ground, so it will have kinetic energy. So at this position B, it will have both kinetic and potential. And then at the point C, it's not exactly ground, just before reaching the ground, its energy will be fully kinetic. It will be reaching with maximum speed, so energy will be fully kinetic, but potential energy will be zero. Okay, now the main point is you have to find out the expression for total energy at every point. Okay, here only potential, here only kinetic, here both kinetic and potential. So I remember I made you do the derivation along with me. So if you want, you go back to those videos and see if you don't remember those derivations. I hope you will remember it. Then this graph tells us how the mechanical energy is conserved. Okay, so there are three lines. So height above ground, energy, and then there are three things you are representing. Potential energy, it increases from 0 to maximum. Kinetic energy comes from, okay, we are talking about this is the case when the body is dropped down, but they have drawn this graph for a body going from lowmost point to a higher point, thrown upwards. Okay, so initially it will have zero potential energy, and then it will have maximum, and then kinetic energy will be maximum initially when you're throwing a body, because you'll be throwing it with a velocity. So kinetic energy will be maximum, and that keeps decreasing and comes to zero. Okay, so potential energy, kinetic energy, but total energy will remain the same. Okay, so okay, if it is a middle point, then x is h by 2, then kinetic energy will also be mgh by 2, and potential energy will also be mgh by 2. You can prove that. Okay, so the conservation of mechanical energy is strictly valid only in absence of external forces such as friction due to air, although total energy is always conserved. The second application that you have is principle of conservation of energy, applying principle of conservation of energy to a simple pendulum. Okay, so again, three positions, mean position and the two extreme positions. So at each position, what form of energy it has, and then total energy. Now in this, you will not have derivation. Okay, so you will not have derivation. You will just say kinetic energy half mv squared is equal to mgh. You need not show how you got it, like how you did for this one. You need not show it this as a different way. Just have to write it, kinetic energy is also equal to mgh. Okay, so I think I remember I marked the points that gives the explanation about what kind of energy is here, what kind of energy is here, and what kind of energy is here. Okay, 1, 2, third point, and then fourth point. And total energy remains conserved again. Okay, now the same two examples, applications can come in the form of numericals also. So you have 6 numericals in this exercise, and everything based on conservation of energy. Okay, I think I have explained everything in detail in the videos that I had put before during the month of May, I think. Yeah, you can just go back and see those videos. I think I've also created a playlist. You can see from that. That will be easy to figure out this particular portion. Okay, so all the best. Prepare well for this test and give your best. See you, children. Bye.